Welcome to this organic chemistry tutorial. Here you will get the chance to revise all of the AES chemistry mechanisms, reagents, conversions, and you get the chance to look at some interesting conversions. Here you will have to write the mechanism for each step 1, 2, 3, as well as finding the missing intermediate. Please pause the video and try it yourself and play as soon as you have an answer. I have a tip for you. Make sure you focus on each functional group at a time. Okay? So think about each functional group and the reactions that you're familiar with. The first one, for example, is an alkene. Okay? I mean, how many reactions of alkenes do you know? Right? So try to retrieve it from memory and then think about, okay, I have an alkene to a bromine. And think if, like, what has changed? It went from an alkene to an haloalkane. So what has changed that has happened? Something has been added onto it. That's why it's going to be an addition. Then you can think about, okay, what do I know about an alkene? I know that has a high electron density. It's going to be a nucleophile. Therefore, the bromine must be an electrophile. But is it just bromine? No, because also hydrogen has been added. So we know that this is going to be the electrophilic addition using HBr. Now, the conditions, I know is an easy one to forget, but remember that when we have halogens, it's at room temperature. Second, this is, I know it's quite difficult, so again, you can think about the functional group and the reactivities that you know, because at the end, I mean, for haloalkanes, how many reactions do you know? Nucleophilic substitution and elimination. Okay, how do you figure it out? Well, again, you can do the analysis of that's the second tip. Think about their reactivity. How do these molecules react? Well, we know that carbon is delta positive and bromine is going to be delta negative. So the carbon is an electrophilic center, so it will be able to react with a nucleophile. So these are things that just can help you retrieving, memory. So then you can think, okay, is it elimination? No, doesn't make any sense, elimination, because it would go back to an alkene. But how do we get to what functional group? Again, think about that, a ketone. So think about the reactions that you know of bromine, and maybe something will come to your mind. Bromine could be the addition of an OH instead. Oh, OH, C double bond O could be related. And then you can think of the next step. So in this case, we are looking at a nucleophilic substitution with, for example, KOH. Now, we have an haloalkane and potassium hydroxide. This reaction will require, as a condition, heat under reflux. Okay. Okay, so what's going to be what is the intermediate? So we know that the OH will go at the same place as the bromine. So this is our intermediate. Okay, and now we can think, okay, what's the next step? Alcohol to which functional group? Again, we think about ketones. Okay, what has happened? Always think about, and that's the third tip, think about the changes. And this can really help, like we've seen for the alkenes. So we had an addition. What changed here? We have more bonds with the oxygen. Addition of oxygen, that's the definition of reduction. Oxidation. So it's oxidation. So oxidation, and then here you do need to remember the oxidizing agent, and one of these ones to remember is potassium dichromate. It's very important with concentrated sulfuric acid, okay, acidified potassium dichromate. And then you need to think about a reaction that requires some time. It's heat under reflux. So if we're heating, we're very likely to do it under reflux. This is because organic molecules, they are flammable. So under reflux would make it much safer. Okay, so nice conversions. Let's go to the next one. This is the second scheme that I want you to try. We're gonna go from an alkane to a carboxylic acid. All of these are reactions that you are familiar with from AS chemistry, so pause the video and try. Remember the tips that I mentioned before. These tips are: think about the functional groups and their activities that you know. Think about the changes that occur. So has it like something being added? Has something been, removed or taken the place of? Or some oxygen added? And then think about the reactivity. This doesn't come to you. Think about what is a nucleophile, what is the electrophile, think about the dipoles, and these should help your mind finding the correct mechanisms. So pause the video, and when you're ready, I'll walk you through the solution. Number one might be the easiest, isn't it? I mean, what do you know about alkanes? There is only one reaction that you know, one mechanism that you've studied. That is the free radical substitution. Remember, very important, this requires UV light and an halogen. Let's say that you want chlorine. Remember, alkanes are really unreactive because there is no difference in electronegativity between carbon and hydrogen, so there is no nucleophilic or electrophilic character, and their bond is quite strong. So it requires something very, very reactive, like a radical, and radicals are generated through UV light. We will look at the mechanism in a bit. Now, what is the product? The product of that is this wouldn't be correct. Notice, because we only have one alkene, so I think it's better HCl, because this will give us only one monosubstituted haloalkane. And this makes sense, you know why? Because you should think about the next reaction. And you will see that if you have a dihaloalkane, how do you get to this without any halogens, right? So think about it. And that's, when you do when you think about the reactivity of the functional group, and then you think about, okay, what's next? Then you might need to correct the reagent that you chose before, okay? Now, we go from an haloalkane to an alkene. You should notice that something has been removed, the halogen. What is that? It's an elimination. I know the elimination, it's a bit tricky to remember simply because it's not like there is something, that reminds us of that, but also a hydrogen is removed. That's why we will need something that reacts as a base. In fact, we're going to need potassium hydroxide, so the hydroxide ion is involved in the mechanism, but very, very important, remember that it's ethanolic, so it's in the ethanolic solvent. Okay, this is done heat under reflux as always, and it's an elimination reaction. So haloalkane to alkene. Okay, how do we go from, and let's look here, alkene to an alcohol? We can't add the OH directly. Water is not very reactive. If we add that, if we have a hydroxide ion, doesn't work because alkene, it reacts as a nucleophile itself, which means that we're going to need another reagent. And this is an important conversion to know. And I know it's not that easy either to remember, but we're going to have two steps. One first step is the addition of sulfuric acid, and it would undergo an electrophilic addition. This will give us this intermediate with the SO4, let's write it like this, HSO4, and the hydrogen. So this is an important conversion because we can get rid of this HSO4 group through a nucleophilic substitution, or better, let's call it hydrolysis. Okay, this is number 4, hydrolysis, okay, with simply warm water. And this will give us an alcohol. Now, how do we go from an alcohol to a carboxylic acid? And now, for oxidation of alcohols is oxidation because I see that there are many oxygens that there are added. So we know that that is oxidation. We know that it depends on the type of alcohol. So we need to always remember the classification. As we see, the OH is bonded to one carbon that has only one other carbon. So it's going to be a primary alcohol. Okay, so primary alcohol, if it undergoes oxidation with, again, an oxidizing agent, so oxidation, and it's going to be the same as we saw before, potassium dichromate with concentrated sulfuric acid, but very, very important, it requires reflux. This is because distillation would give us another product, the aldehyde, but heat and the reflux, it will give us the carboxylic acid because the oxidation goes further. What a scheme was this one, huh? Now, I challenge you to write down the mechanism of every single step that you know. You should be able to do the mechanism of step number 1, step number 2 of our first scheme. And you will be able to do the mechanism of step 1, step 2, step 3. And this should be enough. So challenge yourself in drawing out the mechanisms, and I will help you out as soon as you've tried it yourself. Okay, the first mechanisms that I wanted you to try was the electrophilic addition with HBr. Okay, very important. Let's now be very, very picky with every single step. Important to identify the dipoles. Remember that when the hydrogen approaches the double bond, despite there is not a big difference in electronegativity in HBr, it's polarized, okay? Remember, there is a high electron density in the alkene. Now, we have a transfer of electrons from the double bond to the hydrogen, and the bond to the bromine will break. This will give us an intermediate. Now you have to pay extra attention here because you will see that this is an asymmetric alkene, as in fact we have a CH3 group on one and the hydrogen. So you need to check where the bromine has been added and where the hydrogen has been added. And you will notice that the hydrogen has been added on this specific carbon, which means that this carbon will have a positive charge. Now this positive charge is because the electrons are now from the double bond between the carbon and hydrogen. What happened to the bromine? Well, the bromine now has a negative charge, okay? And that's what will happen after this attack to give us the final product, okay? Now I want you to think about something. Is this the major, or is it the minor product? Take a moment to think about it. Remember that the major and minor product is relevant, of course, only if there is an addition of an hydrogen halide, like HBr, HCl, and if it's an asymmetric alkene. In this case, it is an asymmetric, and we have HBr. Okay, so remember that there are two options for this to occur. So I'm going to do another color. Let's do this color. Okay, the positive charge can also be on the other carbon, okay, where we had the two hydrogens. And this would mean that the hydrogen was added on this side, so the bromine would actually attack on this carbon, okay? So to think about the major and the minor product, you have to think about the stability of the carbocation. So the stability is affected by the number of groups around the carbocation. In fact, if there are many groups, I mean, the maximum groups we could have is like 3 alkyl, like in this example, 3 CH3s. This would be the most stable because it has a stabilization from this, what it's called inductive effect. Okay, so this is stability of carbocation, and it's by inductive effect. Inductive effect, it's when the electron density is shown as this type of arrow, it's donated to a carbocation, or through a bond in general. But this stabilizes it because it makes it more neutral, and that's why this is more stable than a secondary. A secondary would only have two alkyl groups, like two CH3s, and of course, if we have a primary that is just one other alkyl group, it's going to be the least stable. Let's put this a hydrogen. So primary would be the least stable. So the most stable intermediate, of course, is going to be this one, because as you can see, it's a secondary carbocation, which means that it's going to give us the major product. That's why the ones that we drew out, it's the major product. The second mechanism that you had to try out was the nucleophilic substitution from an alkane to the alcohol. Did you try your mechanism yet? If not, pause the video. This is the solution. Of course, this is a very simple mechanism. Why? Because we know that the KOH, it releases OH minus ion. I'm going to write it here, where the OH minus has a lone pair of electrons, and it occurs all in one step. In fact, there is a nucleophilic attack to the carbon that is slightly positive, and at the same time, the bromine breaks. Now, one important thing is that the OH attacks called anti-periplanar, just in terms of direction. You wouldn't be marked down if you didn't, but just, it looks nicer. There is no intermediate in between. Edexcel people, you might know this. Okay, the intermediate looks something like this. So we have basically at the same time that this at the same time that this bromine bond is broken, the bond with the OH it's made. Okay, so we have an intermediate that looks like this. If you've never seen it before, ignore it. And then we have our final product. So for who has to know the details, this is an SN2 mechanism because it occurs only in one step, and A-level chemists, the rate of reaction of this is rate constant times the substrate times the nucleophile. So the rate depends on both the nucleophile and the substrate. That's why it's called SN2. If you didn't know this, just ignore it. You will learn it in year 13. Let's go with the next mechanism. So free radical substitution is not like every mechanism because it occurs in multiple steps, and the steps you can write them just in the format of equations, so structural formula is probably the best way. So we always have an initiation reaction. Initiation is when the chlorine molecule will undergo the homolytic fission under UV light. Okay, if you want to see the curly arrows, what happens in these curly arrows, the homolytic fissions is when, so you don't have to draw the electrons, but imagine they're there, each electron moves evenly. So evenly, the bonds break evenly. Propagation step, it's very important that you remember them and how they occur, because it's always the same, repetitive. So if you have a complex molecule or further substitution, it always occurs in this way. And I like it to remember in this way, that always the HCl is formed, and in the second step it reacts with the chlorine molecule. If you remember this two, everything else should come to you. In fact, we have our molecule, which is in this case, I'm gonna write it as molecular formula, it's okay, C2H6, okay, and this reacts, guess with what? Of course, with the radical that was just formed. Now, if you think about that, the HCl is formed, what does it leave behind? It leaves behind the carbon radical, okay? So we will have a C2H5. This C2H5 is what reacts in the next step with the chlorine molecule, which means that we're going to have C2H5Cl, and guess what does this reform? Cl radical. I think it's important to remember also that these radicals act as a catalyst because of course they're reformed, overall not using the reactions. If you're interested in looking at the curly arrow, I'm going to do a simplistic one over here, highlighting just the relevant bonds. So what happens is that the two radical arrows join to form the HCl bond, and this leaves behind the carbon radical. So you need to show the movement of each single electron. Okay, so I hope this helps. And we could write termination step. Now, termination step in this case, because it was in a reaction scheme, we assume that was the termination step for a very specific product, which is of course the desired product. In that case, we would have the chlorine radical reacting with the carbon radical, with the C2H5. And in the termination step is when the two radicals join to form the desired molecule. Of course, you always have some questions about this, like which other termination step can take place. Remember, radicals, they're extremely reactive, so you could have any combination of radical. In fact, we could even have side molecules like this one. You could even have further substitutions, and this is what makes this mechanism very, very messy. But look at this one. Suddenly we have a big alkene, and this alkene, imagine, can react further with the chlorine radical, and it becomes a big, big mess. Okay, but in general, know one termination step of a side product and the propagation steps. If you remember these key things that I mentioned about, you know that HCl is always formed and it reacts with the molecule in the second step. This should give you a nice head start. The next mechanism is the elimination. We go from an haloalkane to an alkene. So here it uses a base, KOH. In fact, you must remember that in general. Let's put it general as the OH minus ion. Okay, so when it's in aqueous solution, it acts as a nucleophile. While if it's in alcoholic, like in air, let's write it also general. So in alcoholic solution, it reacts as a base. So how does a base react? Of course, it reacts with the hydrogen. So the mechanism, it goes in one single step. The OH picks up a hydrogen. Of course, has to be the hydrogen adjacent to the carbon with the chlorine, because these electrons will move in the p orbitals between the carbon to form the double bond. But of course, carbon can have more than 5 bonds, so the chlorine will leave the molecule. Okay, in fact, we will have, as you can see, as a side product, H2O and Cl minus. Okay, the Cl minus, if you write, if in your equation there is potassium, you would put it, together. But this depends if you write the overall ionic equation or just the or the full equation. So this is elimination, and specifically it's basic elimination. And the very last mechanism for today is the electrophilic addition. Now, I know it looks a little bit weird with this H2SO4. So what helps is knowing the structure of H2SO4. So try it yourself first, and then I will do it as soon as you've tried it. So this is what a sulfate, the sulfuric acid actually looks like. So you need to think about what reacts with the carbon double bond. Of course, it's going to be the hydrogen, because it's delta positive and the oxygen is delta negative. So how does the mechanism go? I'm going to do it very schematic over here. As always, it goes to the hydrogen and then it leaves behind the oxygen, which has a now negative charge. So on one side of the carbon double bond, we add the hydrogen, and on the other side, we have this whole molecule. It's the oxygen that is connected to what was an alkene. Okay, so this is what happens. Of course, remember that there is the carbocation intermediate in between. So please, here I have skipped a step, but we have seen this mechanism. We have seen this mechanism today already. So I hope you are confident with it, and the oxygen is what will bind it to it to give the product. And remember, this is an important conversion, because hydrolysis of this one will convert this one into an alcohol. So very well done today. And today we have revised almost all of the mechanisms, actually I think all of the mechanisms that you need to know for AS chemistry. So well done, and if you have any questions, don't hesitate to get in touch.